Good afternoon. I'm Jacob Thompson, a security analyst at Independent Security Evaluators, and we're located right nearby in Baltimore. We do a variety of software security assessments and occasional hardware for a variety of large and small companies. Did anybody go to the So Hopelessly Broken router competition yesterday and on Friday upstairs? Well, that was also part of our same company, if anyone had gone to that. So this presentation is fighting back against SSL interception, or how SSL should work. But with the poodle bug that came out last week that Google presented, it should be called TLS interception, because SSL 3.0 should be disabled now because of that bug. It's a design flaw. So the title should be revised. So a quick overview here. I'm going to go over the high-level view of how SSL works in normal operation when there's no attack taking place and the protections that it has in place. How SSL interception is performed today and potentially in the future with and without the cooperation of certificate authorities, and how that changes the security model of the internet substantially. Some of the other techniques that have been presented and that are being put in place today by other parties to try and frustrate attempts at doing SSL interception. Then a technology that is out there and known about, but I would say underused, which is client certificates or mutual authentication, and how this, as a bonus, can help us to thwart or prevent SSL interception, or at least make it much more difficult, and a proof of concept website that I've developed that uses this technique. So in normal operation, when you connect to an SSL-enabled server, you're performing encryption. But encryption without verifying the identity of the other party is the classic key distribution problem. Without some form of identity verification, a man-in-the-middle attack can be performed, redirecting your traffic to some third party where they decrypt and re-encrypt it, send it on to the original destination to see what's going on. Normal SSL prevents this by requiring the server to identify itself using a certificate. And a certificate is just, in normal cases, an RSA public key, some identity that is bound to, and a signature. That signature is put in place by a certificate authority. Certificate authorities can be hierarchical. There's a chain in place where one certificate can be signed by another, and so on, until you eventually reach a trusted root certificate authority. The trusted root certificate authorities in your browsers or other software are determined by the company that makes them or built them. Mozilla has a process for determining what certificate authorities are trusted. Microsoft and Apple do as well. So in essence, what happens when you connect to an SSL-enabled server is, has some certificate authority that your software trusts. Is there a chain down to the server certificate showing that through entities that I trust, your identity has been verified, the domain name matches a domain that you truly own. Increasingly, and this is presenting how man-in-the-middle attacks will be prevented. A normal man-in-the-middle attack, if you use software like Burp Suite or Medium Proxy, the reason that you can't use a server certificate is because you need the private key that goes with it to do the SSL handshake. So what this software does is they create certificates on the fly that are signed by some certificate authority, usually just a custom handmade certificate authority that software creates on the fly. It's not trusted because there's no company behind it that's in that list of trusted CAs. So your browser generates a warning when you're using software like Burp Suite. This is showing the client verifying the certificate against that store of trusted CAs. It doesn't work. But increasingly on enterprise networks, a system like this is in place. Because more and more websites have gone to using SSL everywhere rather than just the login page, which was more popular just a few years ago, enterprise networks are concerned, and probably for good reason, about what kind of company data might be leaving their networks over those encrypted connections. You can think of examples like Gmail, Facebook, other social networking websites that have gone to this SSL on everything model. So these companies have bought a system that sits on their network, and as outgoing connections to an SSL site are made, it performs the man-in-the-middle attack. It looks through that traffic for potential keywords, patterns matching credit card numbers, social security numbers, who knows what. Now, they can't do this with that warning on everybody's machine, if you think back to the man-in-the-middle attack. So the conventional SSL interception requires that the company operate this own certificate authority and install that certificate on every single machine on their network. On Windows, they might use something like group policy. Mobile devices, they might use a mobile device management system. Mobile devices and bring your own device are where I believe this starts to become problematic, because your employee's view of who owns the device, off work time, on work time, what if they leave that job and the MDM software is not removed? What if they hand down the device to a sibling or someone else in their family and the software is still on there? I've even thought about what if on off work time they're complaining to some government agency about their employer and that's being captured and logged. There's all kinds of problems that I can contemplate here, but rather than go into those, I want to talk about the certificate authority model and how it is starting to be undermined. Rather than what I just showed you, increasingly this is starting to be the case, where a certificate authority lends its trust out to some entity for the purpose of performing SSL interception. This could happen with or without the certificate authority's cooperation. What a large company can have is what's called a sub-CA. This is a certificate authority that they use internally when they need an SSL certificate, rather than sending individual certificate requests to a public CA and having to do the billing one by one and so on. They will rent out this sub-CA. They're intended to be used only for domain names that the company truly controls. But increasingly what's been happening is those sub-CAs are ending up in these SSL interception devices. 2 years ago, the Trustwave example was where a publicly trusted certificate authority, which was Trustwave, explicitly permitted one of their customers to build one of these devices and put their certificate authority in it for performing this interception and logging. These other two cases just happened in the past year. These both happened without the certificate authority's cooperation. In this case, the company on their own decided, we have this sub-CA, we need to do SSL inspection, let's put them together so we don't have to install these certificates everywhere. Both of these incidents were publicized fairly widely when they happened, and the solution so far has just been legal and contractual restrictions on the CAs. Mozilla is currently undergoing an attempt to rein in their certificate authorities, remind them, no, you're not allowed to do this. But because root CAs are trusted for 10, 20 years, if you look at your list, I think it's going to be a long time before that actually happens. The technical solution that is available but is not used and has some implementation problems is name constraints. Currently, you either are a certificate authority or you're not. Nothing's wrong with a Turkish certificate authority signing a .gov site currently. Name constraints would try to fix this so that when a sub-CA is issued, it can have some pattern in that certificate with wildcards potentially saying only domain names matching this pattern can ever be chained to this CA. That is still years away, it seems. So what are other parties trying to do to make SSL interception more difficult? Google is really taking the lead on this. One of the technologies that they put into Chrome, and Firefox is now implementing as well, is certificate pinning, where on top of the existing certificate authority model, you add another layer of sanity check, where the Google browser and now Firefox are bundled with a list of well-known, high-profile websites and the fingerprints of certificates that are acceptable. If you encounter a publicly trusted certificate that goes to some key or certificate that does not match that pattern, it reports it to Google. That's how the TURKTRUST and ANSSI incidents were both detected. So just to remind these, other than the Trustwave incident, both of these had to be caught and detected after the fact. It's not like a company or CA disclosed like, okay, we made a mistake, we let this happen, let's fix it. Both of these were caught by these mitigations that have been put in place. Another technology is that when the Google search engine is crawling the internet, it keeps a log of the certificates it sees. They do some statistics based on those. The EFF has another project called the SSL Observatory that is similar. They have a big graph on their website showing the interlinks between different CAs and the large companies that possess a sub-CA. Some of them are not even in the technology business, like Ford Motor Company, can sign arbitrary certificates if they wanted to. Another thing that is increasingly common is mobile applications. If you have a native mobile application, you control the SSL library. You can replace the built-in list of trusted CAs with one of your own. If you operate the CA yourself, as long as the private key is not compromised, nobody else can issue a certificate that's trusted against that list. The thing that all of these have in common is that they all operate on the client side. And this SSL inspection model, if you think about it, making it acceptable is all based on having the end user sign some kind of acceptable use agreement that says your traffic will be monitored for unauthorized use, this system uses logging, and so on. Nobody's checked with the server side or the entity operating that server to say, are you okay with us breaking the end-to-end encryption you've been putting in place? So what is something that is not revolutionary but builds onto existing technologies that can be fairly straightforward put in place to try and make SSL interception much more difficult? Is mutual authentication. In mutual authentication, both clients and servers have a certificate. Your server will present its certificate, your client presents its certificate. Both sides have a list of trusted CAs to verify each other. Client certificates are actually used in many cases. For example, in Estonia, every citizen has a smart card with a certificate on it. And many government websites or military websites would be far more likely to use a system like this. As far as public-facing, general public websites, I've never encountered this myself. So what happens in usual when mutual authentication is in place is that there's some third-party certificate authority, just like for servers, that instead issues certificates to clients. This all builds up on the X500 system, goes back a long time. Originally, it was envisioned that the telephone company would maintain some kind of directory of these certificates. It doesn't work that way. So the problem in trying to implement a system like this is that there's no certificate authority that's widely available to issue certificates to clients that users are familiar with, at least. But how, if we implemented mutual authentication, would it stop SSL interception? When this is attempted, the SSL interception device will be able to make a certificate for the server that's acceptable to the client. It controls a list of trusted CAs on the client. But when it goes to make a client certificate that's acceptable to the server, it has no control whatsoever of the list of trusted CAs on that server. So the best thing it can do is try and obtain a certificate from one of those CAs. Even if a commercial certificate authority helps with the server certificate, it doesn't make any difference for the client one. I'm going to present a solution here where we abandon this idea of trying to have some third party authenticate the client before issuing them a certificate. Instead, the server will act as its own CA for the client certificates. If you immediately think about it, the difficulty is how can that server distinguish between the true end user and the man-in-the-middle device? I've thought about an enrollment process where you have some out-of-band channel to exchange a key that makes it difficult but not impossible for this man-in-the-middle device to obtain that client certificate and send its own public key to obtain it. So this is a potential certificate enrollment process. This builds on top of key generation tags that are built into web browsers and have been there for many years, just underused. When a certain form is submitted to the server, the client web browser will generate an RSA key pair, public key, private key. The private key will be stored in some kind of local protected storage. The public key is sent to the server. Then I'm going to send an enrollment key out of band. For this example, I'm using email. For more security, you could use some kind of mobile application that creates some dedicated channel using its own certificate pinning strategy, potentially. Then the server will send the certificate back to the client. Normally, a certificate has no need to be encrypted. It's all public information. In this case, it's going to be encrypted using that enrollment key just for the purpose of making it more difficult to obtain it fraudulently. Finally, the client on the client side in JavaScript will decrypt that certificate using the out-of-band key and install it into the local certificate store. At that point, you can access the website and mutual authentication will succeed. This model is used for Firefox and Safari. On Chrome, it's slightly different because there's no way to install a certificate using JavaScript in the testing that I was doing. I instead encrypt the public key. Once again, it's public information. The only purpose in doing that is that you have to have that out-of-band key for the enrollment process to succeed. I have an example website where this is in place, and I can show a demonstration here. So it's https://mutual.security-evaluators.com. If you try to go to that site, it's going to test your browser to see if you have a client certificate. If not, it's going to put you into this enrollment process. So let's start it. So we have a Firefox web browser open. Yeah. So I'm going to try to go to https://mutual.security-evaluators.com. Now, I actually have two subdomains on this website. Mutual.security-evaluators.com does not require client certificate authentication. I have another domain, www.mutual.security-evaluators.com, that does. In a real system, you would get domains that were far more intuitive as to the distinction between them than that, but in this case, I was able to use the same certificate twice. If we look at this code here, what's happening is it's attempting to load an iframe from that domain that requires mutual authentication. If that had succeeded, that iframe has some frame-busting code in it that would have redirected you to the mutually authenticated part of the site. Because of the same origin policy, I can't determine from here whether that succeeded or not. So I just use a time delay. If this page has not been redirected within 2 seconds, we're going to assume that mutual authentication must have failed and invite the user to begin this enrollment process. So let's do that. What this is going to do, it's prompting you for an email address in this case, for some other method to send you this out-of-band enrollment key. So I will give it an email address. I have a CAPTCHA in place just for sanity purposes for the proof of concept. In a real system, you could say that the CAPTCHA is part of the method that you put in place to make it hard for an automated system to break this. If you answer the CAPTCHA successfully, I'm going to get an enrollment key sent to my email account. All this is a 128-bit AES key that's securely generated. We'll copy and paste it into this form after choosing our browser. When I click this, it's going to cause my browser to generate an RSA key pair. You'll see a dialog flash very quickly. You can barely see it. That actually was all generated by the browser. I did not generate that dialog box. The keygen tag, as part of an HTML form, generates the key pair, includes the private key or the public key in the form submission. But what I did is I've sent that to the server. The server has now responded with an encrypted certificate, which is here. I need this out-of-band enrollment key in order to decrypt that. So I'll put it in. Completely client-side is going to decrypt it and install it into the browser. Once again, I didn't generate this dialog box. When the server or client receives the certificate with the correct content type, it's going to immediately install it in the certificate store. We can verify that by going to our certificates list. This, for a digression, is the list of trusted certificate authorities. You can see this TURKTRUST is still there. The French Certificate Authority, which I can't remember its alphabetical name, is still there. So what is the penalty when a certificate authority violates its trust model and allows some entity to generate fake certificates? Nothing, in the long term at least. My client certificates are listed under this tab. This shows the certificate that the server issued. If you look at the certificate authority that issued it, this is not a publicly trusted certificate authority. There's no one for the man-in-the-middle device to go to and convince into issuing a fraudulent client certificate. Now that I have that certificate in place, if I try to go back to the beginning, which you can see the URL at the bottom, this time that iframe will work. This is another dialog box that the browser generated itself. It's saying, the server you're connecting to has presented me with a list of acceptable client certificate authorities. You have a matching certificate. Do you want to use it? Or if you have more than one qualifying certificate, please pick one. In this case, we only have one. Well, I waited too long. This time, the mutual handshake worked. The server was able to generate a web page containing information from that client certificate. In a real website, you would use that to allow the user to bypass some security process, or at least record the fact that they successfully authenticated using a client certificate. I have much more confidence in this authentication or login session. Now, comparing this to some of the other security measures that a lot of websites have put in place, security questions, security pictures, one-time passphrases, all of those work within the SSL session. So a man-in-the-middle device can see all of those going past. Security questions, I think, are even worse than passwords, because if you've answered it truthfully, it probably never changes. They're used across multiple sites. These devices that are sitting in the middle will be able to see the answers. So if you want to try out this website, you just go to mutual.securityevaluators.com. If you go to justsecurityevaluators.com and click on knowledge, there's a write-up explaining many more details and implementation issues about this. In the meantime, does anyone have any questions? Yes. Right, so you could go in two directions. One is you add a more sophisticated channel like that RSA token, so long as it's not just a number that's submitted over that channel that's being intercepted. What I'm envisioning this out-of-band channel does is, if you're an entity trying to perform some kind of large-scale SSL interception, and you have to break that out-of-band channel every single time, one, it's going to be hard to do that robustly. Right, so you've got to break different kinds of email systems potentially, get it at the right time. If you go through this enrollment process successfully on this network, and then I move to your network and it's already happened, the client might be tipped off that they're being forced through the enrollment process again. But the overall view is, I'm believing here that you might be pushing that entity into having to perform a phishing attack or some other kind of more active attack that legally could put it across the boundary, that people might have the ability to complain about it. Anybody in the back? Yeah.
So if I'm understanding correctly, there might be a scaling problem because you have to take the enrollment process in every one of those sites.
Right.
Which makes me think, what about an escrow or a clearinghouse in that back end that says, for these 100 sites, we all have to share the same user ID and do enroll as one.
Right.
It works with all of us. Are there any downfalls to that?
Well, I agree that this is convoluted, but more and more, a lot of websites are starting to do this one-time passcode anyway with your email. So I wouldn't say it's that much worse. As far as the single sign-on, is what you're basically proposing, I think it would make it much more usable should the single sign-on entity be trusted, right? So now you've reintroduced this problem where there's a third party that could be willingly or coerced into issuing a certificate fraudulently. However, if single sign-on can work between Facebook and people that trust them, or between Google and others that trust them, there's no reason you couldn't build a client certificate model on top of that sign-on system. Yes?
What do you think companies respond to? Does this allow any sort of encrypted connections where they're saying like fraudulent acceptance?
Well, they could do a couple things. Already they have the capability to whitelist banking sites that they don't go through this device. They could do that. Otherwise, you're not creating any kind of bypass for the system. In fact, this whole process will fail if one of these devices is in place. So you're basically cordoning off your server from entities that are going through an SSL interception system. So the worst that it can do is break functionality on those networks, cause people to start complaining. I don't know that they would try to stop people from doing encryption, right? I mean, what would be more likely to cause them to do that is if you do some kind of making your own secure channel in JavaScript, that now you have the crypto.js stuff, that might start happening as well. I think that would make them more alarmed than SSL, which can be broken in a pretty standard way if you have these certificates in place. Any questions from this side? Okay, I guess we'll close it down then.